All right, so it's a pleasure to have Professor Fonseca back with us today, and she's giving her fourth lecture in the series of 5 lectures. So her next lecture will be next week. Okay, that's the last one. And thank you very much for everyone for coming, and thank you, Professor Fonseca, please.
Well, thank you for having me back, and thank you all for putting up with me for 3 lectures already, today 4th, and next week the last one. And again, Happy New Year. It's never too late to say that. So it's been a while. I think the last one was on December 9th. So I have to do a little bit of recap. I won't spend too much time on that because the lectures are on the web and everything is available, but still I just want to refresh our memories. And so let me start by recalling. And you know, as before, don't hesitate to interrupt me if I go too fast, or if there's something which is not clear. By the way, so remind me, this goes until 3:40, is that correct?
Yeah.
3:40, okay. Okay, so I want to remind you that we are dealing with this energy that looks like this. If this, okay, that looks like this. And that's, and again, I probably said it several times, but I say it again. This is a prototype model, but in general, you could have something much more complicated of the type 1 over epsilon f of x u epsilon grad u, right? So it could be something coupled. In my case, I have decoupled, right? I have the potential decoupled from the gradient and everything. It's nice. And the gradient basically as a Dirichlet integral. Well, okay, it can be much more involved than that. But the tools are basically the ones I'm explaining now. Then you have to adapt them to the coupled case. But the ideas are the ones, the main ideas are the ones that I am exposing to you. Okay, and so this is for U in W12 of omega, which sometimes you also write this as H1 of omega. It's a Sobolev space. And again, you recall what that means, right? This means 2 things. This means that on one hand, U is in L2 of omega. So if you wish, the integral of U squared dx is finite. And on the other hand, it also, so that's an and. You have that gradient of U is also, which now is going to be L2 of omega with values in Rn. And so basically the grad U squared is finite. That's what W12 stands for. And in addition to that, we are also assuming that we have a mass constraint, which is that you have in addition that the integral, the average of U is some fixed number m. I'll set it to be plus infinity otherwise. And the m here is going to be a number that is going to be somewhere between the 2 L's of W. W is the potential well, right? So that m is going to be somewhere in here, in what is we call the Spinodal region, which is in between the 2 low energy phases. And by fixing that, I'm forcing that I'll need to have a mixture. I cannot have just zeros and just ones. I'll need to actually have both zeros and ones. Okay. And as before, omega here is an open bounded domain. Okay. And so the set of zeros of W is 0 and 1. Again, this could be more general than that. You could have finitely many zeros, right? Not necessarily 2. You could do it for finitely many, but let's keep it simple. Let's keep it to 2. So what we were doing last time was we would fix epsilon positive, and we wanted to prove existence of minimizers of at least a minimizer of I epsilon, which I would call U epsilon, right? And for that, we use the direct method of the calculus of variations. And so the first step, I remind you, in the first step, you consider an infimizing sequence. Which I call, so this is for epsilon fixed. So I will index, I'll put as an upper script the n, so that's a sequence in n, right? So in other words, if I take the limit as n goes to infinity of this energy, oops, and epsilon, what I get is the inf of I epsilon of v, where v are in W12, and the average of v is what it should be, which is that number m, which is fixed a priori, okay? Then on step 2, which is something we already did, was to prove compactness. In other words, that we can find a subsequence, which now I index as nk, so it's the index in k. So it's a subsequence of this one. And there exists indeed some target, which I call W epsilon, which is going to have the right average, and such that U nk epsilon converges weakly to U epsilon weakly in W12. And that means, well, actually, as a consequence, you have two properties. Someone needs to be admitted. Okay, you have two properties. One is that that's so-called Relic Conduction theorem that says that at the L2 level, actually you have L2 strong convergence. Okay, so UNK converges to UNK epsilon, to U epsilon strongly in L2 strong. And at the level of the gradients, you only have weak convergence in L2. And I remind you that what that means is that every time you take a test function phi, which is in L2 of omega with values in Rn, if you integrate grad UNK, which is a vector, in a product, you clean it in a product with phi, so that's a vector times the vector gives a scalar, that should converge to the integral of grad U epsilon in a product with this. Okay, that's the conversion. Okay, so all this was done, and today we are going to start with step 3 of the direct method, which is that which amounts to showing that I epsilon is sequentially weakly with respect to L2. Your topology is in L2. Lower semi-continuous. And again, that means that anytime that you have a sequence Vn that converges to V, it's actually W12, sorry. Not L2, it's W12. In W12 weak, then I epsilon of V should be below the limit inf as n goes to infinity of the I epsilon. Epsilon is fixed. Eventually, I'm going to let epsilon go to 0, but not yet. Okay, so that's what, and we know that from the direct method, with these 3 steps, step 1, step 2, step 3, will tell you that the U epsilon, which you found on step 2, indeed is a minimizer, right? So if so, then we'll know that I epsilon of U epsilon is indeed the minimum of I epsilon of V over all V, which are in W12 with the right average. Okay, and then you're done. Well, done at the epsilon level, right? Then you have to work harder to get rid of the epsilon, that dependence. Okay, so actually this step 3, as I wrote, has nothing to do with the sequence of minimizers or the subsequence. This is a general statement that applies to any sequence that converges weakly. Epsilon is fixed. Well, of course, in the end, I will apply to this particular subsequence, or to this one, right? But this is a general statement. This is a general statement that applies to any sequence, right? In particular, you take it to be this one here. Right? Okay. Very good. So okay, so then let's prove that. Okay, so why is this? So consider one such sequence Vn. So again, by Relic-Kondrachov, I know that since the Vn converges weakly to V in W12, by the way, I'm taking omega to be a nice, I should say, Lipschitz domain, because I want to apply all these theorems from Sobolev spaces. This is a Lipschitz domain. So in particular, I want to use Relic-Kondrachov. That is, weak convergence W12 implies strong convergence in L2, actually even better than L2, L2 star, but it's okay. It's a Lipschitz domain, right? So the boundary of the domain locally stands to one side of a Lipschitz graph, of the graph of a Lipschitz function. So we have this. So again, this implies, as I said before, 2 things. One, that the Vn converges to V strongly in L2, and that the grad Vn converges weakly to grad V. So that's weakly in L2, just as I wrote before, and that's those 2 bullets that you have before, right? Okay, now every time that you have, so this effect, if you have a function f that goes, say, well, in this case, everything is scalar valued. So from R into, say, non-negative, this can be much more general than that. And by the way, all this theory of logarithmic continuity and for energies and all that, well, okay, it's a bit self-serving, but Giovanni Leon and I have a book on that, so you can find all these theorems there, much even more general than that. But in particular, if you have a convex function, and I already mentioned this before, this effect that if you have a convex function, and if you have Vn converging to V, well, let's put it this way. Let's put it actually Rn, because I'm gonna, oops, Rn, and say, suppose that you have a Cn vectors in Rn converging to C in L2 weak of Rn, then we know that the integral of f of C of x dx is below limit inf of the integral of f of Cn of x dx. Actually, that's an if and only if. If you have a function f, an integrand f, for which every time that Cn goes to C weakly, you have logarithmic continuity, the integrand needs to be convex. So this is actually an if and only if. Okay, it's a full characterization of convex functions. Okay. Oh, okay, so that is good, right? Because definitely f, the square is convex, right? And so we have that we have weak convergence here. This is convex. So I know that the integral of grad v of x squared dx is going to be below limit inf of the integral of grad vn of x dx. Okay, that's good. But remember, our energy I epsilon has two pieces to it, right? It has this one and it has this one. Epsilon is fixed. Epsilon is a perimeter at this point, does not go anywhere. Okay. Now, on the other hand, we know that Vn converges to V in L2 strong. So up to subsequence, which I will not relabel, I know that I have pointwise convergence almost everywhere. So for almost, Ln is the Lebesgue measure, right? For almost every x in omega. Okay. And so this is an argument we used before. W is continuous. So you can use Fatu's lemma. To say that the integral of W of V of x dx, well, that's actually the limit by continuity, right? Because you have pointwise convergence and continuity of W, right? Well, obviously, this is the same as the limit inf. And now you use Fatu's lemma. W is non-negative. And so you go up. Right? Okay, so then conclusion. Remember, this is what I want to show, right? I want to show this. Whoops. So I'm going to start from the right hand side and try to get to the left hand side, right? So that's what I'm going to do. So therefore, if I take the limit inf of I epsilon of Vn, right? That's the limit inf of the integral of 1 over epsilon W of Vn of x dx plus epsilon grad Vn of x squared dx. And I don't need this parenthesis here, right? Well, this is, of course, the limit if I can break this into a sum of the two. And why don't I put the perimeter outside, because that is not going anywhere, plus an epsilon okay, so the limit if of the sum is bigger than or equal to the sum of the limit ifs. Okay, but now we are good because we have two pieces here. One was the lowest mid continuity of grad square, and two was the lowest mid continuity of the W's, right? So you put 1 and 2 together, right? You use this fact and you use this fact to say that, okay, so that's bigger than or equal to by 1 and 2. 1 over epsilon W of V plus epsilon grad V squared. Well, okay, and that's exactly I epsilon of V. That's the functional, and you're done. Okay, very good. So we know that for each level epsilon, we have a minimizer U epsilon. Now, if you go back to lecture 2, if I'm not wrong, we had the roadmap there. And in particular, I think I call it, it was like step number 2 or something, where there was a claim. And the claim said that, oh, once I have this sequence of minimizers, one minimizer for each I epsilon, then I can prove that up to a subsequence, the U epsilon, which I will not relabel, the U epsilon converges in some sense, which will make precise. I mean, the topology, I make precise later on, to some U. And actually, this U is going to be a function of bounded variation with values in 0, 1. You may also recall that back, I don't know, I don't remember in which lecture, we proved that if you had, we proved something like this. We proved that if you had the supine epsilon of I epsilon of U epsilon, which I would call a certain number M, if I would have that finite, and if I had that the U epsilons were converging to some U pointwise almost everywhere, then we proved, and here we used a prototype I call WT, which was something like T squared, 1 minus T squared, and we also used Fatus. We concluded that the function U would need to have value 0, 1 almost everywhere. This is something that we established before, but there were lots of ifs, right? It was, oh, okay, if I have, so these are ifs, right? So if you have this, and if you have that, then you have this, okay? So there were lots of ifs in there. There was this if, there was this if, and there was this thing. Okay, there's also, part of the work is already done, because I also proved with an ansatz by using a good competitor, I also proved that if I had a minimizer, I knew that I would have this, right? So recall also that we showed that, again, it's a big if U epsilon minimizes, then indeed the soup is finite. This is something we already did, okay? And so here, so if I prove that up to a subsequence, U epsilon goes to U, in some sense that implies pointwise, then you can come down here and say, oh, I already proved this, but then I have pointwise convergence, so then I know that my U will have to be in 0, 1 anyway. Okay, so a lot of the work is done. So basically, we already proved this implication. This is done. We already proved this. Okay, which is, that's what you have here. So right now, this is what you need to prove. We need to prove that my subsequence converges somewhere. It converges in some sense that implies pointwise convergence almost everywhere, right? I already have, that's minimizer, I have all that. Okay, so to do, So our sequence of minimizers U epsilon converges in particular pointwise almost everywhere, and after extracting a subsequence, if necessary, to some mu, which is going to be a function of bounded variation. And again, the fact that lives in 0, 1, it will come for free. That's been done already. So the point is the convergence, right? So this is, it's this, and that you have that. So I'm going to give you two proofs. One, which is doesn't quite, well, it works, but I will cheat a little bit, and then I'll give you a proof that's actually correct beginning to end. But first I want to give you a feeling of why this is going to work, because the fully rigorous proof uses the argument, except it's more careful. So I'm going to do the following. So I'm going to define, and you're going to see this later on in the rigorous proof. So I'm going to define the function phi of t, which is the entire derivative of square root of W of SDS. Makes sense. Remember, W is an energy density. It's non-negative, right? So this makes sense. Then I'm going to define V epsilon to be the composition of phi with my sequence U epsilon. So what happens? Then if I take grad V epsilon, chain rule, right? So you're going to get phi prime at U epsilon times grad U epsilon. So that's the square root of W of U epsilon times grad U epsilon, right? It's an indefinite integral. That's calculus. Good. Okay, so I'm going to give it, let's see, I'm going to give it a name. Well, let's call it 3, since I already had a 1 and a 2 before. And now, okay, this one I'm cheating. And I say, oh, you know what? Without loss of generality, false. This is false. But let's pretend for a moment. I can assume that my U epsilon lives between 0 and 1. So basically, you have here, okay, so this is 1, this is 0, right? And my U epsilon could be something like this, then it could be like that, and then it could be like this, and it could be like that. And basically what I'm going to do is I'm going to truncate it, right? I'm going to say, you know what, if it was not, this is basically what we call the Spinodal region here. And I'm going to truncate, so I keep it between 0 and 1 as it is, but then as soon as I go up, I will replace by, I truncate it, okay? And look, why do I say without loss of generality? Because morally, I have no interest to go below 0 or above 1, because W likes to live between 0 and 1. And when you look, so say if I would call this U epsilon bar, which would be the truncate, maybe I should put it in green. If I call this the truncation, U epsilon bar, you calculate the energy of U epsilon bar, and you say, oh, okay, so there where U epsilon is below 0, I truncated by 0. So W it's W of 0, right? There where U epsilon is between 0 and 1, I didn't touch it, right? There where U epsilon is bigger than 1, oh, I have another 0, because that's a well of W. W of 1 is 0, right? And also, if you look at the gradients, well, same thing, right? Because the gradient, you're replacing it by 0, gradient of 0 is 0. in between, you're not doing anything, so that's good. You kept it the same way. And then again, where u epsilon is bigger or equal to 1, you're taking the gradient of 1, which is 0. So that's definitely bigger than or equal to, less than or equal to, I'm sorry, I epsilon of u epsilon. So u epsilons were minimizers, remember? So u epsilons were minimizers. So if I was going below or above, one of these terms would be actually non-negative. So I would get here a strict inequality, right? Because one of these would be, so either these or that would be strictly positive, right? If I was really below or above. And so I would pick up a strict inequality contradiction. Why do I say that this doesn't work? Because by doing this truncation, so that's why you have to be careful, because the average of this new function may be different from M. I may mess up the average, okay, with this truncation. And remember that I'm working with functions which have that average, because if I don't fix the average, then why not putting u epsilon to be 0 all the time or 1 all the time? Your energy is 0, right? You're not forcing to have a mixture. But by keeping this average, I need to have a phase transition, right? I need to have a free discontinuity. And so, but that's why this argument set is cheating, because yeah, sure, okay, but you messed up the average, right? So you know, it's not admissible. But let's pretend it's okay, okay? And let me finish the argument. Why is that? So if I assume that I have this that I'm lying between 0 and 1, let's see why this goes through, and then I have to fix the proof, right? Okay. So what do I have? So remember that we already proved that plus infinity is bigger than this this I epsilon of I epsilon. That was something that we proved before, maybe lecture 1 or lecture 2. Okay. And again, let's write what that is. That's I of epsilon, W of u epsilon, plus epsilon grad u epsilon square dx. That is what I call, I'm going to call this an a square. I'm going to call this a b square, and I'm going to use Young's inequality, or if you wish, Cauchy-Schwarz. Right, so a square plus b square is going to equal to 2ab, right? And so that's going to be bigger than or equal to, and this is the so-called modica mortale trick. So that's bigger than or equal to twice the integral of, now you see the epsilons cancel out, right? The epsilons cancel out. You get a 1 over epsilon and you get, right? So you take the square roots and they cancel out. Okay, but remember 3. This quantity in absolute value is exactly the absolute value of what I call V epsilon. That's by 3. This is going to be twice the integral of grad V epsilon. Okay, so then what do I have? Remember that V epsilon is, there's a very nice, phi is a nice continuous function. I'm assuming that U epsilon is bounded between 0 and 1. So then V epsilon is going to be bounded, right? It's a continuous function of a bounded function, it's a continuous, right? bound in L infinity. In particular, it's bound in L1. Right? Okay, but now by, let me call it 4. So by 4, I have that grad V epsilon is bounded in L1 of omega with values in Rn. So in other words, you have that V epsilon is bounded in the subolar space W11. Now, I'm just going to put the alarm for me so that I don't get distracted here. Now, W11 is not reflexive. And so, say if you were in W12 or W1P for P bigger than 1, you could say, oh, okay, so then I can extract a subsequence which converges weakly in this space, right? W11 doesn't work. Like by the same token, if you have a sequence body in LP for P bigger than 1, you can extract a subsequence that converges in the same LP weakly, but not in L1, right? Sequences body in L1 do not necessarily converge weakly in L1 because they may have concentrations, right? However, they are weakly compact, if you wish, in the space of bounded variation. So this implies that there exists a subsequence, which I will not relabel, such that V epsilon converges to some V in BV weak. And what do I mean by this? I mean by these several things. First, I mean that the function V is a function of bounded variation. And that means two things. One, that V is an L1 function. And two, means that the derivative of V in the sense of distributions is indeed, it's actually a Radon measure. And I don't want to spend too much time on this because it's not the crux of the problem here. But basically what this means is that for all I between 1 and n, and for all test function phi, which is say C fit with compact support in omega, if I integrate V times d phi dxi, well, this would be dv dxi times phi if V was smooth, right? Because you integrate by parts and the integral on the boundary 0 because the function, the test function has compact support. But that's not the case, right? My V may not be, actually it won't be because it has only two values, 0 and 1, so it's not continuous. But what it means is that I can write this as an integral of the function phi against a Radon measure mu y. And so what you do is that you identify the partial derivative of V with this measure mu y. That's essentially what you're doing. That would be another lecture. I don't want to spend a lot of time there. But the point is that, yes, there is a notion of convergence here in that, so I know that my target is going to be a BV function, which is a nice function. And the good news about this convergence in terms of BV weak, so maybe I should tell you what is this convergence, right? And so BV weak convergence means two things. Convergence means first that the V epsilon converge to V in L1 strong, therefore apt to extracting a subsequence. So without loss of generality, I may assume that I have pointwise convergence. because I have strong convergence in L1. For almost every point in X. And it means that okay, well, if you wish, it means that if I look at the gradients, again, I don't want to go too much into detail. If I look at the measures which have density grad v, the grad v epsilon is a real gradient. These are nice functions. These are sublevels functions. If I multiply these times the Lebesgue measure restricted to omega, I would have a weak star convergence to the, say, the derivative of this derivative, which is this. In this generalized sense that I introduced there, it goes so weakly star in the sense of measures. But don't worry about that. I don't need that. But this is important because remember that I told you before up here that there was this if, right? I need that the convergence gives me pointwise convergence. And then you say, oh, wait a second, but this is not U epsilon, this is V epsilon. We have to go back to the epsilon. Yes, you're right. Okay, so let's do that. So again, I remind you that the function phi is the integral between 0 and t of square root of W of S ds, right? And definitely between 0 and 1, this is a strictly increasing function. Not afterwards, because afterwards W plateaus at 0, right? So you have to be careful. But this is strictly increasing. Everything to me is happening between 0 and 1 because I truncated. I'm actually working with that U epsilon bar in my mind. I truncated, I cheated, but that's okay. And then you say, oh, okay. So then U epsilon. So remember that phi V epsilon was phi of U epsilon. So you can invert. So U epsilon is phi inverse of V epsilon. But this function phi, the inverse is going to be increasing. Also, it's going to be continuous and everything. And you have pointwise convergence, right? So this converges pointwise to phi inverse of V almost everywhere. And that's what I define to be my function U. That's how I define U. My target is going to be phi inverse of the V that I found. That's my U, and then you're done, and then, okay, then the rest is done because you already know that U has to be between 0 and 1, etc. Only value 0 and 1, etc. Okay, so this would end that proof, except that I truncated and I messed up the average. Okay, so then let's backtrack and let's say, okay, so now I'm going to fix the proof. But the idea is here, and the idea is going to be to use this Young's inequality or Cauchy-Schwarz inequality, and to reduce this to an energy that has no epsilons. The epsilons canceled out, right? So you see here, where was that? Where did I do that? Cauchy-Schwarz, here, you see? Right here, there are no more, there are no I mean, these parameters are gone. And now I just have functionals of functions. Okay, so so now I'm going to offer you the correct proof. It's not much harder, but you cannot use truncations. Okay. So Okay. Now, actually, I'm going to be a little bit more general than this, because remember, you see, to prove that that my sequence converges somewhere, I never use the fact that U epsilons were minimizing sequence. Well, okay, I used to truncate, right? But anyway, the truncation is out the window. What I really used though was this fact, right? Because I got the fact that this was bounded. Actually, let me put it like this. So epsilon prime. So for epsilon fixed, I had that. So you get that in particular, the integral of grad v epsilon is bounded by that m over 2, right? So this is actually what I used, was the fact that I had that this energy was bounded. And so this one was bounded from above. That was what I used. Okay. The minimality was to truncate, but I insist that it doesn't work. So what I want to show, so let's ask the question again. So suppose that I have, say, a sequence epsilon n that goes to 0, and suppose that the sup in n of some sequence un is finite. Okay. What I want to prove, so my claim, is that I can find a subsequence, say UNK in K, such that UNK converges in a one strong, which is actually what I needed, right? Because then I can take the pointwise convergence to U for some U. Okay, it's going to be in BV, but L1 would be enough. Okay, so that's what I want to prove. And I'm going to do that. Now, you see, I cheated. But on the other hand, the only thing I used about W was that it was 0 at 0 and at 1. I didn't use any growth conditions on W or anything, right? It was basically zero hypothesis, except continuity. Now, there's a price to pay. I need to assume something. And I'm going to assume that, as before, that W is continuous. So that's hypothesis 1, which I used before, but this is a new hypothesis, namely that W grows at least linearly at infinity for all t with t bigger than some L, and this is true for some C positive. So at infinity, you need to grow at least linearly. That's perfectly reasonable. I mean, the energies usually they explode actually, right? As the phase field goes to infinity. So with these two hypotheses, we have a claim to prove. Am I right to say that I'm at the end of my time? Basically, right? Okay, because I don't want to start this proof.
Yeah, sure,
Because this proof will take a while. Okay, that's my alarm. So this proof will take a while, so I don't want to go through that. So that's going to be so next time. So next time we'll prove this. So we'll finish this proof. And then you may recall that I still owe you the gamma convergence, right? That was, I told you that this was gamma converging to some functional I, which was a constant times the perimeter, the surface area of the interface, right? And this has two parts. There's a gamma limit inf, and there's a gamma limit sup. So next time, I don't know if I have time to do the gamma limit soup, but at least I want to do, I'll definitely finish this proof here, the compactness with the correct proof. And I want to give you at least the gamma limiting for the gamma convergence. Time permitting, I'll give you the gamma limit soup, but I don't know if I have time for that. Okay, and this is a good place to stop. So I'm going to stop here.
Thank you very much.
So I don't